Hi everyone, I'm Zach, and today I'm going to be showing our team's final project for ECE 5730. So the idea behind our project is we want to study how sound can be localized in a binaural system. So for example, we humans have two ears. How do we determine where any arbitrary sound originates relative to our point of view? So what we wanted to do was to see if we can come up with a hedge transfer function that could reasonably predict a set of angles, namely the azimuthal and the polar angle, given a stereo audio input. So stereo because we would have one microphone for each of the ears. So in terms of the hardware, this is our circuitry. There are a couple of different components here. We have a SD card reader, which helps us read data from a micro SD card, where we store our sound primitives, ones that we synthesize using Audacity, as well as store recordings that we do with the microphones. And then there's also a DAC. It's a 16-bit DAC. 4 of those most significant bits are for control. So we effectively have 12 bits for audio payload. And since all the audio files we synthesized were 16 bits, we had to do some processing to convert between the two formats. Because of that, the fidelity kind of degraded a little bit, but we kind of countered that by using a guitar amplifier, which did improve the fidelity quite a bit, as well as brought the volume to a reasonable level for recording. We also have a serial debugger, which we use to set up a serial interface to control the flow of the program, namely starting and stopping the recording, choosing what primitive we want for playback, as well as specifying the angles. This is the dummy head that we 3D printed. The idea is to emulate an actual human head with actual human ears, since what we got from our research was that the structure of the ear canal itself has a lot to do with how we localize sound. So we wanted to capture that effect here. We didn't take sight or visual cues into account for this project, since that would really complicate things due to ventriloquist effects and things like that. So that is the hardware part. Also for inside each of these ears is a microphone hooked up to two GPIOs, physical pin 31 and 32, which should be mapped to ADC0 and ADC1. So those are two different ADC channels. The RB2040 itself only has one ADC unit. So in order to simultaneously pull data from each of these microphones, we had to multiplex between the two GPIOs or ADC channels to achieve that. So after we've successfully collected all of the data, which in total were about 500 different wave files, we moved on to do some data processing in Python. So we start off by doing a short-time Fourier transform on all the audio time series that we captured in 1.1 second chunks, and then computed the power spectrum. And then in order to be sort of perceptually accurate, we did a MEL spectrogram transformations. The reason for this is our hearing is actually not linear. Our hearing is logarithmic, and the MEL spectrogram can represent that nature of our hearing. All these DSP operations were done using the Python librosa library. So by the end of all this data processing, what we effectively had was a matrix of 3 different spectrograms. One spectrogram of the left ear, one spectrogram of the right ear, and the difference between the left and right ear spectrograms, which we hope to represent the interaural level difference. And another nice thing about doing this MEL spectrogram transformation is that it really reduces the dimension of the data input while also being a lot more perceptually accurate. And then in terms of model construction, we have a neural net that's 3 layers, nothing too complicated. This is what the initial model looked like. And we actually had to remove some of the initial operations since after trying to load up the model on the RB2040 using the TFL Lite micro library that Raspberry Pi made available to run TensorFlow models on microcontrollers, we realized that some of the operations that we use, namely the Licky Relu, was not available. And we also had to remove batch normalizations since it incurred a bit too much memory consumption during inference. If we could go back to the beginning, we would have definitely chosen to use the RB2350 instead, not only because it has a lot more memory, but also because it's capable of doing float point arithmetic. Something we realized too late into the project was that all the DSP operations that we did in Python using librosa was by default done in float32, and the DSP library that we use on the RB2040 was the ARM CMSIS DSP library, and although it does support float32 operations, it was not available on the RB2040 because it doesn't have a float point unit. So given that constraint and the time limit we had, we kind of settled on just doing all the DSP on our laptops. And after the training of the model, this is what the validation looked like. We can see that the correlation is pretty well for the azimuthal predictions. So azimuthal being the horizontal orientations. And this is the elevation validation, which still is pretty good, but not as good as azimuthal. We always knew from the beginning that elevations is harder to determine. Azimuthal, that can just be the interaural time difference or interaural level difference, but elevation requires a lot more analysis of the frequency spectrum to determine the canal peanut cues. And then after removing some of the operations that were not available in the Pico TFL Lite micro library, this is our final accuracy, which you can see that is worse, but it's still decently but it's still decent. It's still possibly correlated. So we can move on to doing a little test to show how audio can be captured using this head structure, and running a prediction on that audio input to see if it can correctly predict where the sound came from. So let me just insert the SD card into the micro SD card reader, and then I'm gonna load the code onto the board. So the file system is mounted. I'm gonna choose the sound primitive, and what I'm gonna do, what I have here is a guitar amplifier. I'm gonna try to play the sound from sort of the top right direction of the head and see what we get from it. Okay, I'm gonna unmount the SD card, insert that back to my laptop, and then so this is the wave file that captured the recording that we did. I'm just gonna quickly move it to a folder that my Python script recognizes. I'm gonna clean up my folder real quick. Now I should see, yes, corrected WAV file. I'm gonna rename it to test, and then I'm gonna run my prediction here. Okay, so the prediction gives us that it gives us, there are two different predictions. There's one that's the Keras model output, and there's one that's the TFL Lite model's output. And the TFL Lite model is basically the model that's converted from the Keras model so that it can be compatible on the RB2040. So we have two predictions. The Keras model gives us the 7 and 1 indexing, and the TFL Lite model gives us 310 indexing. So let's see what that says. Let's see what that shows. So let's say my sound source is directly facing the head. So based on the prediction 7 1 1 2 3 4 5 6 7 and 1. Based on the Keras model's prediction, the sound sort of came from the top left of the head, which is incorrect. And then the TFL Lite model's prediction gives us that the elevation indexing is 0 1 2 3 and 9. 0 1 2 3. So it tells us that the sound kind of came from the top right, which is the correct prediction. So it's kind of interesting that the TF-Lite model gives us a better answer, even though it has been sort of converted from the Keras model. The Keras model is the original model. So in terms of work to be done, we have quite a bit of work to improve the accuracy of our models, and as well as in terms of the hardware, we want to actually use a more capable microcontroller to be able to do real-time audio recording, inference, as well as float 32 DSP operations, so that it's better for the prediction and data processing, consistent with the librosa operations that we did in our Python environment. So for more information on the project, please take a look at our documentation website. There are more explanations and visuals on the documentation website. Thank you all for listening. That is our project.